Okay. I repeat the last paragraph. Welcome to the 37th of the International Association Congress of Housing Science. That has been organized in Santander by the University of Cantabria and its group of Building Technology of the Faculty of Civil Engineering. At the opening session at 10:30, between 2 hours, the institutional authorities who will chair the act will explain in detail the genesis, development and scope of this Congress. Now, let's focus on this first session, plenary session. I present you the professionals who chair with me the session. They are representing the entities that have sponsored the conferences that they go to introduce. Before mentioning their names and titles, I would like to thank for your support, which has been fundamental and decisive for this Congress, for having a high professional and scientific level. The professional authorities who are with me are, for the first conferencia, will be presented by courtesy of IDICO, and the presenter of the speaker will be Ingeniero Javier Yuste Navarro, director de la Unidad Técnica de Investigación en Seguridad y Tecnología de la Construcción. The speaker will be Professor Federico Mazzolani. The second conference is courtesy of the College of Architects of Cantabria, and the speaker will be presented by Don Ignacio Pereda, the Dean of this professional college. The speaker will be Professor José María Ezquiaga. And the third conference will be presented by courtesy of the Consejo General de la Arquitectura Técnica de España. The speaker will be presented by the Vicepresidenta del Consejo, Doña Rosa Remolá y Ferrer, and the speaker will be the technical architect, Don Carlos Aymat Escalada. So we go to present the first conference, and Javier, when you want.
Good morning, ladies and gentlemen. Like said Luis Villegas, my name is Javier Yuste. I represent INDICO in this Congress as responsible for research in safety and technology. I'm a civil engineer, and first I wish to thank the Congress organization, especially Professor Ural and Professor Villegas, University of Cantabria. Without their effort and dedication, this conference would not be possible. Also, appreciate the confidence placed in IDICO as partner, hoping that there was positive our modest contribution. Only to indicate that IDICO is a non-profit society constituted like a technological center pertaining to the Technological Institutes network of the Valencian community, which has the support of our regional government. It's a great satisfaction for me to present at this plenary session the participation of Professor Dr. Federico Mazzolani from the Naples Frederick II University. I want to thank in my name and the entire organization to Professor Mazzolani the great attention and kindness that has been adjusting their schedule to come to Congress. It is difficult to summarize in a few minutes his teaching, professional and researcher career. Full professor of structural engineering in the University of Naples, president of the Doctoral School of Civil Engineering, also president of the Master in Design of Steel Structures since 2006, both at the University of Naples, Frederick II. His main research activity focused on structural analysis and design, steel and aluminum structures, earthquake engineering, seismic design, structural upgrading and consolidation, historical construction, and upgrading with innovative materials. With more of 700 papers in journals proceedings, 49 monographs, 34 books, etc. He's a Doctor Honoris Causa of Polytechnical Universities of Bucharest, Timisoara in Romania. He has a Masonet Award to 2001. He's chairman of different European committees, the ECC, ESTC, 13 Committee Seismic Design, Chairman of the National Mirror Committee for Eurocode 3, Eurocode 4, and Eurocode 9 in aluminium structures, Chairman of the Coordinator of the different research European projects like ILVA IDEM, seismic upgrading of reinforced concrete buildings, protection of historical building by mixed and reversible technologies, Chairman cost of G26 on urban habitat construction under, etc. Finally, is member also of the Canadian Standard Association, the International Association for Experimental Structural Engineering, Royal Academy of Engineers of Czech Republic, no, Royal Academy of Engineers of Spain, Academy of Engineers Czech Republic. Well, no more words on my part. I call on the Professor Mazzolani with his lecture titled Protection of Historic Buildings, and I thank all people for this Congress and starting the Congress. Thank you very much.
Mazzolani, please.
Good morning, ladies and gentlemen. I have the privilege and the honor to be the first speaker of this conference on the subject which is related to the protection of historical buildings. And in particular, I would like to give you information about the result of an international project, which acronym is PROHITECH. The meaning is Earthquake Protection of Historical Buildings by Reversible Mixed Technologies. 7 countries from Europe participated: Italy, Belgium, Portugal, Macedonia, Slovenia, Romania, and Greece, together with 5 countries belonging to Mediterranean area: Morocco, Egypt, Israel, Algeria, and Turkey. In total, 16 institutions belonging to these countries participated to this project. 4 from Italy, 2 from Macedonia, and 2 from Romania. In total, 12 countries plus 16 institutions. We create a kind of network around the Mediterranean basin. We have to consider that this area is characterized by a very high seismic risk due to the conflict of 3 plates: Eurasian, Arabian, and African plates. And you consider that in that area there are so many buildings belonging to the cultural heritage with different features and different styles. Consider the fact that there are at least 2 or 3 or more religions in this area. The common point of this project and the key word is reversible. Reversibility is a property very important in this kind of intervention. Reversible mixed technologies come from a matrix of mutual cooperation among materials. Consider the possibility to have a new material for consolidation which can help the old material which are damaged. And we create in this way a kind of new composite materials. The PROHITECH activity developed since 2004 up to 2008. And every year, for the first output was devoted to the state-of-the-art dealing with intervention strategies. The second deliverable was devoted to identification of innovative material and techniques in order to identify among them the so-called reversible mixed technologies. The third part is the most important one because it's devoted to experimental and numerical activity in order to set up calculation models. And the last part is give the validation criteria and design guidelines which are applied to many study cases. I would like just to mention some important issue of the experimental activity. Look the materials, look the color. We consider masonry in the form of stone or adobe, wood, reinforced concrete, and iron or steel. And we test different kind of level, full scale and large scale, of models, of substructures, and of devices. If you look at the color, we have considered the green is for masonry, orange for wood, yellow for reinforced concrete, and blue for iron. You can see how the tests have been distributed among the different partners. Just Israel and Egypt didn't make any experimental activity. We start from tests on devices and substructures. For instance, we tested magnetorheologic dampers at the Second University of Naples, or we tested special dissipative torsional links for timber structure. We tested this specimen in our department at the University of Naples. Or we tested also dissipative panels which are used as a damping element in structural applications. And look, this timber building is a building which was damaged during the earthquake in Turkey, 1999. And we think that if you have used this kind of special metal panel as devices, this building didn't collapse. And at the university, Boğaziçi University in Istanbul, we tested timber frames which were reinforced by metal panel and submitted to horizontal forces. In Naples, we propose a new composite system made of timber, steel, and light concrete by using this kind of connection element like steel leaves which are surrounded to the old wooden beams. We test different type of connectors by using different materials in the interface between the sleeve and the timber, and we tested the full-scale element in our laboratory. We apply this technology, this new system, to the wooden structures of the Royal Palace in Naples. In this very important hall, which the structure is sustaining the frescoes on the top of the room, and we apply this kind of system in order to connect the horizontal floor and the vault. In case we have timber beams with rectangular cross-section, we use different type of connector, and we tested this type of composite system at the University of Lisbon. In Timișoara, Romania, we tested the possibility to have steel shear panels connected to the masonry. We made a diagonal test together as also panels submitted to horizontal forces. You see one side there is the metal panel, and on the other side we apply the horizontal load and we obtain a given result. In general, we increase both the strength of the panel, but also in particular ductility. Very important is the experimental and numerical activity on large-scale structure. This is the Mustafa Pasha Mosque in Skopje, built in 1492. We decided to make a model of this structure, and the numerical models were used for the prediction of the behavior of this monument. And we built the model in scale 1 to 6 by using the same stone as the original mosque. And the final model is very well, done, and also with the minaret. We tested this, and we damage, and after we repair by means of FRP wraps on the top part and FRP rods in the mortar joints, using a system we have already applied in another building. And now there is a movie. After repairing, the model was also damaged again and tested again until the collapse. You can see the weakest part is the connection between the upper dome and the bottom walls. It was very satisfactory for us that the cultural heritage authorities in Macedonia use the same system we have proposed for reinforcing the real mosque. Nonlinear models, numerical models, have been also used for interpreting the results of this test. The second large-scale model is the Gothic cathedral of Fossanova. It's in Italy. It's south of Rome. It's a typical Gothic, Italian Gothic. It's not a Gothic like in Spain. It's not so splendid, and it's like a little more calm. And we built the model by using, in this case, an artificial stone, considering the scale, the reporting scale, also in strength. The model was in scale 1 to 5.5 in order to exploit all the dimension of the shaking table. And it was designed piece by piece and built in a very, very careful way. Look, this fantastic model seemed to be really a Gothic cathedral. It was tested and repaired by using, if you want, a traditional system, because you use ties, but not only ties at the bottom of the arches, but also on the top of the arches. And we put also vertical ties in the columns. This was very important, because with this system we increased 3 times the capacity of the structure. And we obtain the final acceleration, 0.40 g, which was perfectly predicted by the numerical model. Look at the last phase of the shaking table test, which has been done at the Skopje ISIS Institute. We applied the Kalitri earthquake registration, which started with a first quake, and after seemed that everything is finished, but after this more strong quakes arrive and produce the major damage. You see. The third model was a Byzantine Basilic St. Nicola. In this case, we apply a very special type of seismic protection. You know, base isolation is very common by using rubber bearing. In this case, we isolated the structure by means of water in pressure, the water below the model. You see the model is like in a swimming pool, and a small pressure isolates the building from the quakes. In this condition, by using the maximum power of the shaking table, we were not able to produce any kind of damage to the structure. And of course, we had also Greek partners, and the Greek temples was another subject for a large-scale model. And you know the importance of the connector in the architraves on the top of the columns, and it's easy to demonstrate that the presence of this connector can avoid the collapse of the temple. And, but you cannot use iron or steel because of the corrosion. The corrosion can produce more damage than the earthquake in some cases. And we use special devices for connection, which are made of stainless steel or titanium. And we built 3 columns by using the same marble as in the Parthenon, coming from the same mine. And in scale 1 to 3. In the Parthenon are 10 meters. We use 3 meters and 30. And we test these columns in the shaking table of the University of Athens by considering 3 types of configuration. Isolated columns, or columns connected with architrave in lines, or in a configuration in a corner. And we test with and without connectors on the top of the architrave. We test also full-scale structure, and we had the possibility to use this. I received this reinforced concrete building as a gift in the area which was dismantled in the old steel mill near Naples. We consider reinforced concrete also an historical material, because all the 20th century is characterized by reinforced concrete buildings. And there are many architects that produce very important works in this material. And we built a special retaining walls structure in steel structure, and we apply a cyclical load in total of about 300 tons. And we produce a damage to this building which corresponds to an earthquake with a return period of more than 3,000 years. So we were very strong in producing this damage. But after we decided to repair, and we have repaired by means of these special devices, which is a kind of bracing, but in a special bracing which is called BRB, buckling restrained braces. It means that this device cannot buckle. It works in the same way as in tension and in compression. It means that one diagonal per each mesh is enough, and we accommodate this diagonal inside of the gap of the 2 masonry panels of the external claddings. And really we obtain a very satisfactory result with using this system. The final output of this project are 6 volumes. The first is devoted to the intervention strategies which are used in the seismic areas of the Mediterranean basin. Volume 2 is devoted to reversible mixed technologies, which are identified as an innovative system for seismic protection. In Volume 3, we have all the experimental activity imagine that this volume is 900 pages, only this one, and in total 6 volumes are 4,000 pages. Volume 4 is devoted to the numerical activity versus calculation models, and number 5 provide the guidelines in the protection of historical buildings, and number 6 is a collection of study cases. In total, the contribution of the researchers coming from the 12 countries participating to this project, in total 150 researchers, 2 minutes. Many PhD theses were developed in this, at least 10, in this, during these 4 years of the project. And last year, I organized a conference in Rome in order to disseminate the results of this project. And we have the participation of additional 40 international countries. And with the contribution coming outside of the project, we published 2 volumes for a total of 1,700 pages. Thank you very much.
Thank you very much. Professor, thank you for your brilliant conference, for respect